Let me do the opposite problem of what we were doing on Wednesday. Pick a vertex, find me things that are furthest away. How do we know which vertices are furthest away? So I pick a vertex U, and I ask which vertices are furthest away. Is the eccentricity of? I'm measuring from U, which should be the eccentricity of U. But that number could be anywhere between the radius and the diameter, right? So there's quite a bit of range there to figure out what's furthest away from any given vertex. Okay. Wednesday, we described the center of a graph as what vertices? Aha. But if it's the lowest eccentricity, then it's equal to the radius. Okay. So let's look at the maximum instead of the minimum. If I look at the vertices whose eccentricity is as big as we can get, then I'll call those the peripheral vertices. Center, edges. We've used the term edges. I don't want to use the term edges again. So the outskirts, the peripheral area, far out as I can get. In the same way that we then said the central vertices give me a subgraph called the center, the peripheral vertices give me a subgraph called the periphery. So CEN was center, PER is periphery. Here's the same graph as the textbook example for center from Wednesday. And in this graph, we found that the center was these two vertices. So go back and look in the notes or in the textbook. What are the eccentricities? Or let's just do it right now. What are the eccentricities of these vertices? What's eccentricity again? It is not 4 for each vertex. There are different values here. Definition of eccentricity is the shortest of the longest paths. The eccentricity of V is the distance between V and a vertex furthest from G. So you have to know how far the furthest away things are. And here's this example. Oh, well, that was stupid of me. I left off an edge. No wonder I wasn't getting the right number in my head. I left off an edge. So this is 2 because I can get to any vertex in 2 steps. Same thing down here. 3, 4, 3, 3, 4, 3, 3, 3. Talk to me, Jonah. You're looking at me like I'm an alien. Okay, let's start at the upper right corner. What vertex do you want to get to? 1, 2 steps. Pick another vertex. How about this one? 1, 2 steps. How about this one? 1, 2 steps. 1, 2, 1, 2. It's never more than 2 steps away from anything. It takes a while to percolate out from every vertex. It really does. So in this case, what are my peripheral vertices? Just the 2 separate vertices with 4. So the periphery, if this is my graph G, the periphery of G consists of 2 isolated vertices. I'll label them. Now, I did say that we were looking at the periphery of a connected graph. Why do I need that? You've got vertices in different components. We said we could either say the distance is undefined or it's infinite. Then I don't have a maximum, do I? And then every vertex in one component is infinitely far from the other component, and vice versa. The maximum distance is automatically infinity, and the periphery is every vertex. That's not helpful. Build another graph. Pick a cycle. Of at least size 3. I'm sorry? Doesn't matter. Any of them. What do we know about the eccentricities in CN? Wednesday. We worked this out. I know the eccentricity exactly. Thought it was less than that. Floor of n over 2. Because you can go halfway around from either side, and that's the furthest away you can get. Regardless of whether it's odd or even, you just round down. Wait a minute, that means that every single vertex in the cycle has the same diameter. Sorry, the same eccentricity. What's the periphery? The whole graph. But it's also the center as well. There's an illustration in the book, K6 inside C6. Yeah. That's disgusting. I've got a connected K6 in the middle. I've got a cycle on the outside. And like with the Peterson graph, I'm connecting the outside to the inside. But then from the outside, I can get to any vertex inside in one step. 1 and then 2. To get back to the outside, I need to cross one of those in-to-out bridges. So from outside to outside takes me 3 steps. Even if I go around or across the middle, takes me 3 steps. Every vertex on the outside has eccentricity 3. Every one on the inside has eccentricity 2. I've got a clear center and periphery. Gee, I wonder why they call them that. The middle and the outside. Questions? We showed on Wednesday, mentioned, that any graph can be the center of some graph, right? There's a way to take any graph and make it the center of something. We added like 4 vertices and then built some extra edges. What about periphery? Because that would be an equally interesting idea. Is there a way to build another subgraph so that the one I'm looking at is the outside edge. And I build inward. Well, the answer turns out to be no. Bialik and Sislow would prove that a non-trivial graph, G, is the periphery of some graph if and only if one of two things is true. In other words, in the periphery, I either need every graph to have eccentricity 1 or none of them to have eccentricity. What? I was able to construct from the graph the new graph where I had that as the center. So I would like to know, if one of these conditions is true, how do I build the new graph to get the periphery? So let me at least do that part of the proof. Start with one of these conditions and end with, hey, this is the periphery of something. Okay, if every vertex in the graph has an eccentricity of 1, what do I know about the graph? Got to be complete. The shortest path from anything to anything else is one step. Everything has to be directly connected. Wait a minute. If it's complete, then I know the eccentricity, they're all 1. The graph is its own periphery. The diameter is 1. The graph is its own periphery. I knew self-centered made sense, but self-peripheral sounds absurd. All right, let's switch it. So that's if this condition was true. What about the second condition? No matter what vertex you pick in the graph can't be complete. There's some other vertex not adjacent. Okay. I'm going to add one vertex to my graph. I'll call it W. And I'm going to join it to all of the other vertices. V of H is V of G and W. How do I build the edges? Build the edges by taking all of the edges that are already in G and then connecting every vertex in G, W. Now, let me think about the eccentricities. In my new graph H, what is the eccentricity of W? I took my entire graph G, and I added this one vertex, and I connect everything in G up to this vertex W. What is the eccentricity of W? 1. You get to any other vertex from it. Now, pick a vertex that was in G to start with. What's the furthest distance to get to any other vertex? Up to W and back down. Can it ever be 1? Why not? Because it wasn't 1 to begin with. That should be a 1 less than. Looked like a K, I realized. So E of GI is equal to 2. Wait a minute. If the eccentricity of G is always 2, then G is the periphery. The only other vertex is W. These are the ones with the biggest eccentricity. Ta-da! If my graph is complete, it is its own periphery. If my graph is incomplete, add one vertex. Connect it to everything. There's another analysis topology idea here. Remember we said that a metric distance was a topology idea, an analysis idea. What we've just described is adding one point is making an object compact. Those of you who dealt with me dealing with limits about infinity, and I said what you could really think of is that there's really only one infinity. It's at both ends. Whether you go off to positive infinity or negative infinity doesn't freaking matter. Just do this, put your hands over your head, poof, the two ends of the number line touch, and there's your point at infinity. You've added 1 point and turned what was an infinite line into a circle, which is nice and compact, isn't it? Adding one point is an important idea. We'll see it more later in a lot of different classes. Going the other way is not much more difficult. If I have a graph that is the periphery of something else, then there'll be some vertices with degree 1 and some not, show that I can't make the periphery. So the other version is done by contrapositive. You want to see that one? Go read it. Hey, wait a minute. This guarantees me at least one whole category of graphs can never, ever be the periphery. What whole category of graphs fails to be a periphery? What cycles are there on periphery? Yes, but I was only really looking at connected ones in the first place. There's a whole other category. Where's a graph where I'm guaranteed to have some vertices that have eccentricity 1 and some vertices that don't? I don't know about that. Maybe not all trees, but certainly trees that are small. Binary tree, right? I think I'm drawing them wrong. Let's draw this one like this. What kind of graphs are those? But the top is always 1. That vertex has an eccentricity of 1. All the others have an eccentricity of 2. To get from the top row to the bottom row is 1 step. To get from any vertex in the bottom row to any other vertex in the bottom row is 2 steps. Some vertices have degree eccentricity 1, and some have eccentricity 2. So any bipartite graph, K1S, a star, 1 in the middle and the rest around the outside, K1S is never the periphery of any graph. Questions? Abigail, you're looking at that kind of if you talk to me. Okay. 2 on it. In a connected graph, I can fix a vertex. So let's start with a connected graph, G. Nail down one of the vertices, call it U. and find me the vertices that are furthest away. Find me the set of V. Well, let's just find one to start with. Find V so that that's the one furthest away from you. Again, we said that didn't have to be unique, but it could be. Then just instead of describing eccentricity, we can describe eccentricity of U. Make sense? This is a spot furthest away from you. There could be more than one, right? If we do this for every vertex in the graph, we may find that some vertices are furthest away and some are never furthest away. An eccentric vertex of the whole graph means it's eccentric for some vertex U. I would like you to write next to each vertex its eccentricity. For the moment, just do U, V, and W. Jonah, you were asking me how to figure this out. So pick one and we'll do it together right now. Okay, because that corner, right? But I do 0, 1, 2, 3, 4, 5, like layers out. I'm sorry, say again. 1, 2, 3, 4, 5. It's the furthest possible distance to anything, not just to V. What about V? I'm sorry, who said? 4. And U? So E of U is 3. I clearly see a vertex that is 3 units away. Yes? The distance from U to V is 3. So V is eccentric to U. But the eccentricity of V is 4. So V is eccentric to U, but U is not eccentric to V. This is not a symmetric relation on vertices. Okay, wait a second. E of V is 4. What's 4 units away from V? W is. U is only 3 units away. So in spite of the fact that V is the right distance from U, U isn't the right distance from V. Because it doesn't match the eccentricity. Something else further away in a different direction. But it has to be, if the eccentricity of Y has to be bigger than the eccentricity of X for Y to be eccentric to X. Because this X furthest away thing is Y. But there might be things further away from Y if I go in a different orientation. I can't get any further from X. So this can't be any smaller. Because the distance from X to Y is at least this number. If I have a vertex and it's peripheral, what do I know about the eccentricity of this one? It's the diameter. But that means there has to be some vertex that is that distance away, right? That's the maximum possible distance. Wait a minute. That's the biggest possible distance there is. What's the eccentricity of Y? Because we know right here it's got to be at least the same as the eccentricity of X. But that's the maximum eccentricity we can have. Hey, wait a minute. In the periphery, all of those vertices are eccentric to each other. Every vertex in the periphery is an eccentric vertex. Every peripheral vertex is an eccentric vertex in a graph. Not necessarily the other way around. There's a box in the middle, and then connections to diagonal corners. It's a bow tie with a jewel in the middle. Page 335, figure 10. I'm going to write the eccentricities. Okay. The periphery consists of the two edge vertices Q and R furthest out. Yes? That's the periphery of G. Sorry, H. Periphery of H. That means that Q and R are eccentric to each other. Q is eccentric to R is eccentric to Q. They're the right distances. Is T eccentric to anything? Is there some vertex that is the right distance away from T? Jonah? To get to Z, I've either got to go to W and then to somewhere else. Well, okay, Z, you're right, T, Z to T, right? And T to where? What's distance 3 from T? Well, T to U is 2 steps. But if that's 2, then this is a third step, isn't it? So R is eccentric to T. T is eccentric to Z. T is an eccentric vertex. But if T is eccentric to Z by symmetry, V is to W, S is to Y, U is to X. Well, that means these 4 are all eccentric. They're eccentric to these. Well, wait a minute. That means the list of eccentric vertices is now much larger. I've got 6 eccentric vertices. Q, R, T, S, V, and U. What about W, X, Y, and Z? Is W eccentric to anything? What? To get from R to W takes 2 steps. That would make R eccentric to W. Is something eccentric to, is W eccentric to something? What is something that it takes me 2 steps to get to R? I'm sorry, 2 steps to get to W. Change letters. What is something that takes me 2 steps to get to W? Perfect. That means W is an eccentric. W is eccentric to Y. Okay, by symmetry, if W goes with Y, X is eccentric to Z, and Y is eccentric to W, and Z is eccentric to X. Wait a minute. The set of eccentric vertices is all of them. Oh. Every vertex is eccentric to something, but only 2 of them. Peripheral. There's more on eccentricity. Now, clearly, being eccentric doesn't mean that the eccentricities are equal. And I don't even have constant eccentricity here, but everything is eccentric. There's a lot more to come on this. We'll continue this on Monday. Have a wonderful weekend. I will see you then. Quick, before it gets too much darker.